Good evening, everybody. Okay, can you guys hear me? See the screen?
Yes.
Perfect. All right. So how's everybody doing?
Good.
Doing all right.
Okay. So we're going to jump right into this. We were talking last time about how to find axial forces and reactions on a bar that is indeterminate. So we were looking at problems where a bar is wedged between two walls and it is first degree indeterminate, but there are tricks and tips on how to come up with another equation. You only have one equation to solve for forces in the x direction. How do you come up with a second equation to solve for two unknowns? And so we had started an example problem walking through that with the what's known as the compatibility method, and we're going to jump right into that. Now I backed it up just a little bit so we can kind of get a basis for where we started. So we're not just jumping in completely into ice water, completely cold. But before I get started and picking up where we left off last time, are there any questions from me? Okay. Oh, for number, how do we estimate the box amount under the curve? 3, 6. What was 3, 6? Okay. Yes, yes, yes. So it's asking for the modulus of resilience and the modulus of toughness for the material. Okay, I've had several questions about this, and there's, I guess, two basic ways to solve it. You can't get an equation for that second part of the graph, the line that goes basically from 0, 0, 3, 5 to 0 0.28. Which is most of the graph. There's no equation for that function, so we really can't integrate it. So the two ways that I know of solving it, the way that I solved it, was at each grid at 0, 4, 0, 8, 0, 12, 0, 16, at each one of those straying grids, I ran my finger up that black line until it intersected the curve. And then I guesstimated as best I could at what that stress is at that point. I basically just eyeballed it and interpolated it. So for 0, 4, for instance, to me that looks like about 57 KSI. So then I took each one of those grids and I drew a straight line from 0, 4 grid to 0, 8 grid and created a trapezoid. And then I got the area of that trapezoid by the distance and strain, 0, 8 minus 0, 4, times the average of the stresses. And that way you can get the area for each one of those columns, and then you add them all up for the total under the curve. So that method is basically eyeballing KSI on each grid and then finding the area of trapezoids. The other way to do it is to find the area for one grid. So basically, one grid is 10 KSI high by 0.04 inch per inch wide. And that's the area for one square. And then you count up the squares. And that on its face might seem easier, but the hard part is when you get to the squares that the curve is intersecting, what proportion of the square is under that intersection. So then you have to kind of eyeball, is that a quarter, is that a third, is that a whatever. So, but that's the other way to do it, is to count up all the squares. Does that answer your question? Okay, great. Any other questions before we get started? Okay. Excuse me. That's the worst when you just get started and your voice starts cracking. Here we go. Picking up from where we left last time. And like I said, I'm going to kind of start the example. I went back about 10 slides so that we're all on the same footing. So for the compatibility method, we're going to start by exploring an example as shown. Here was our example. So this is a bar wedged between two walls. It is 1 degree indeterminate, so we cannot solve it just using summing the forces and finding our reactions. So the area of A to B is the same as the area from B to C, 2 inches squared. Modulus is 29,000 KSI. The goal is to find the forces in the bar and the reactions. And I am going through this a little fast because I'm going to get to the point where we left off last time. So if I cut a free body diagram of segment A to B, then I have some unknown force in this free body diagram, FA of B. By isolating the segment AB, we can see that it's an unknown force. I draw it because I assume it's in tension until I know otherwise. That is acting over the length of A to B. If A to B was an isolated member, then that force AB would cause a deformation delta AB as shown, just like that. Because the force AB is constant over the length AB, how do I know it's constant? There's no other forces acting on it between A and B. So the force has to be constant from A to B. Because the force is constant over the length of A to B, we can use the deformation equation, where delta AB is FAB L over AE. I put in the values that I know. I know the length, I know the area, I know Young's modulus. I do not know F of AB. So I solve it and just leave FAB in terms of FAB. Now we look at segment BC, and I have a force BC on it. And then I consider it an isolated member, then the force BC would again cause a deformation delta BC as shown. And delta BC is FBCL over AE. Again, I plug in what I know, and I solve it in terms of FBC. Now for the compatibility part, the two segments are attached at B. Therefore, one segment cannot deform relative to the other segment. Therefore, the deformation of AB plus the deformation of BC has to equal 0. That is not to say that node B doesn't move. Node B may move around, but whatever grows on one side, it has to shorten on the other side because the overall distance from A to B is constant. It can't change because it's wedged between the two walls. And I just said what I was going to say. Okay, so by this equation here, AB is equal to negative delta BC. And so I can plug in what I know. Delta AB is FAB over 1611.1. And FBC is minus over 2416.7. And that came from this equation and the one on the slide before. So I can equate to 2. FAB is equal to the negative 1611.1 over 2416.7 FBC. Now I have an expression that relates to two internal forces by rigidity. Now I have two equations for two unknowns, and now we can solve for our reactions. The first equation, of course, is summing the forces in the x direction equal to 0. The second equation is this one that we just derived that relates in a proportion. FBC is proportional to FAB. Okay, so that's where we left off last time. Any questions? Okay. So now, looking at the global free body diagram, since we have two segments, we can make two cuts. So I have an unknown force between A and B, and I have an unknown force between B and C. So I'm going to make a cut between A and B and another cut between B and C. Looking at the first segment from A to cut 1, so this segment right in there, I have an unknown end reaction, RAX, and I have an unknown internal force, FAB. So I sum the forces in the X direction. I've got them both drawn to the right, so RAX plus FAB equals 0. RAX equals negative FAB. And that's pretty much all we can determine from that first cut. The second segment from A to cut number 2 looks like this. And let's see. Oh, because the end reaction is equal to negative FAB, then I plugged in the negative FAB right here for that end reaction. And then I have 6 kips, and I have the force BC here. Summing the forces in the X direction, I have minus FAB plus 6 kips plus FBC equals 0. But FAB is equal to negative 1611.1 over 2416.7 FBC. So I substitute that in here, plus 6 kips plus FBC equals 0. Now I only have one unknown in my equation. I can solve it. So FBC is equal to negative 3.6 kips, and the negative means it's in compression. I assumed it and I drew it to be in tension. It is negative, so therefore it is in compression. Now I can go back to this equation here and plug in minus 3.6 into FBC and solve for FAB. FAB is a positive 2.4 kips, so FAB is in tension. And then going back up to the top here, RAX is equal to negative FAB, so it's equal to negative 2.4, which means that it is the opposite direction than what I had assumed. So RAX is 2.4 kips to the left, not to the right. Okay, I want to reiterate, when you are solving for internal forces, they are either positive or negative. Positive means tension, negative means compression. When you are solving for end reactions, those are not compression or tension. Those are either in the direction that you assumed or they're in the opposite direction that you assumed, indicated by the arrow. Okay? So make sure you understand that internal loads are positive or negative, tension or compression. Reactions, which are external reactions, are denoted by a direction arrow. And then likewise, I found my reaction at CX is 3.6 kips also to the left. And that should make sense, right? The reaction on the left plus the reaction on the right had better equal the total loading on the whole system. So the whole loading is 6 kips. The total of the reactions is also 6 kips. And I boxed my answers, and that is it for this example. Any questions?
Sorry, can you just go back one slide real quick?
I'm sorry, go ahead.
Can you just go back one slide real quick?
Sure. Right there?
Yes, thank you.
Okay, let me know when you're good.
Okay, you're good. Thank you.
Okay. All right, so that was known as the compatibility method. And it's known as the compatibility method because it hinged around node B in the middle. And it said, if member AB was free to move, how far would it deform? And if member BC also was free to deform, how far would it move? And then it's compatibility because the total movement has to equal 0 by compatibility. The B from the left has to be the same B as from the right. That's compatibility. The next method is known as the flexibility method. And this is a little different, but it gets you to the same place. So the flexibility method, if I look at exactly the same problem, and the area AB is equal to area BC, 2 inches squared, modulus is 29,000, same 6 kip load on a 5-foot long rod. However, the flexibility method, we're going to start by releasing the support at C. And it could be A or C, it's kind of arbitrary, but I'm used to looking at it from the C side. So if we release the support at C, then we just have a free rod, 5 foot long, with this axial load, this point load on it. And with this point load on a rod that is free to deform, you're going to get some deformation out here at the end of C when you release it. So that's denoted delta C, and the little f there stands for free. So if C is free, that's the deformation you're going to get. Okay, so again, the whole concept is you take something that is a little too complicated to just directly solve. So we're going to break it into 2 bite-sized pieces. The first bite-sized piece is releasing C and solving this as if it was just a free rod. So if we take a free body diagram of A to B to C and find our reactions at A, then this is our free body diagram. And basically from this point on, for axially loaded indeterminate members, I'm going to neglect the shear and the moment at A, as it's obvious that those are trivial and are 0 force members. So we just left those off for clarity. But I do have a horizontal reaction at A, and I have a load at B. There is no reaction at C because it's been cut free and free to deform. So sum the forces in the x direction. I have Rx plus 6 equal to 0. So Rax is going to be a minus 6 kips to the left. Now, since we have 2 segments, again, we're going to make 2 cuts, one between A and B, one between B and C. So if I look at the first segment from A to 1, I have my 6 kip reaction on here that I solved for. And then I have an internal force FAB that I have not solved for yet. It's unknown. Sum the forces in the x direction, and I get FAB minus 6 kips equals 0, FAB positive, 6 kips negative. So FAB equals 6 kips in tension. Looking at the second segment from A to cut 2, my end reaction, my load, my unknown force FBC. Sum the forces in the x direction. I have FBC minus 6 plus 6 equals 0. Therefore, FBC equals 0 kips. No force in FBC. Okay, so now that I have my results, I can summarize them with an axial load diagram. So between A and B, I have positive 6 kips. Between B and C, I have 0 kips. So this is my axial load diagram describing the internal load for the entire length of this member. And again, as you can see, the load is constant from point A to point B. Okay, so the deformation at C, delta C free, is equal to the sum of, from 1 to 2, I only have 2 segments, of PL over AE for each segment. You have to sum up each segment independently. So segment AB is a positive 6, the length is 36, over 2 times 29,000. For segment BC, I have 0 kips, but I put the rest of it in here for completeness. So 0 kips times a 24-inch length over 2 times 29,000. And that gives me a real number. So 0.003724 inches. So again, remember what we're doing. If C was released, then under a 6 kip load, node C would stretch out by 3.7 thousandths of an inch. Now we must find the restraining force. Node C cannot really move 0.037 inches to the right because it's restrained. That's the real problem. So we find the force required to bring the node C back to 0 deformation. This force is known as the restraining force. Okay, so here's my free body, or here's my problem. And now I have to push this rod back. I stretched it out when I released C, but now that C is not really released, I have to squeeze it back until I get exactly back to where I started from at 0, because that's where it ends up being by definition. So how much force does it take to squeeze this whole rod back to a 0 deformation? At this stage, we do not consider the loads that we applied on here. Those were already considered when we released the rod. Now we're just looking at how much force does it take to squeeze the rod back to where it started from. Okay, so no 6 kips at this stage. This is deformation at C, and then the R stands for the restraining force. And this is my restraining force, FCR. Okay, so by definition, however far this thing stretched out when it was free, it now has to get squeezed back by the restraining force. And these two have to be exactly equal so that I get right back to 0. Okay, so my delta restraining is the negative of my delta when it was free. So delta restraining is minus 0.03724 inches. Delta is equal to PL over AE. P then is equal to delta AE over L. So my restraining force is equal to delta CR AE over L, which is minus 0.03724 times my area 2, my modulus, over the entire length of the rod, because it's being squeezed back all the way to the support. So 36 plus 24, and this equals minus 3.6 kips. Now, a free body diagram of the whole body. And I have 3.6 kips squeezing in on C. I have an unknown RAX at A. And summing the forces in the X direction, I have FAX equals 3.6 kips to the right, resisting this load. So now we need to find the internal force FAC. We only need one cut because anywhere on this rod would work. Then I draw a free body diagram of ABC. And so I have my in reaction, my unknown FAC, sum the forces. FAC is equal to minus 3.6 kips, or it is in compression. Draw an axial load diagram. And here's my axial load diagram for Now remember, this is the restraining force. This is only half of it. This is my axial load diagram for the restraining force. Now, to finish up the problem, by superposition, we can add this load diagram to the first diagram we found by releasing C. So this was the first diagram we found. This is the second diagram that we found. And adding the two together, I get 6 minus 3.6 is 2.4. 0 minus 3.6 is minus 3.6. Before I do that, let me go back here. So it shouldn't be surprising. We get exactly the same answer as we did using the compatibility method. I'm going to stop for a minute. Anybody have any questions for me? Yep, a lot of steps.
Which method do you prefer using?
I'm sorry, Adriel, is there a problem that you can only use flexibility? Okay, you guys are all kind of asking on the same lines. The flexibility method or the compatibility method give you the same answer every time. So it is up to you. I present both of them because one of them is shorter. It has less steps. But in my humble opinion, I find that the flexibility method is a little easier to visualize. So if you're having trouble visualizing it, it's easier to understand the concept of releasing one end, let it stretch out, and then squeeze it back to where it started from and add it all together. So more steps on the flexibility method, but again, my opinion, easier to conceptualize, less steps with the compatibility method, but if you get kind of boogered up and start drawing things backwards, you might get more lost. So that's why I present both. The textbook presents both. Totally up to you guys, whichever you'd like to do. Okay, so who had, I'm sorry, I walked all over the question. Who had a question? It was a verbal question.
Oh, I just asked like which one you prefer doing.
Oh, okay. I'm sorry. Yeah. I think I prefer the flexibility method. And when we get to the next section, where we're going to talk about thermal stresses and strains next, and then we're going to wrap it all up by talking about forces and thermal together, that's where it really gets kind of head scratchy. It really kind of gets kind of hard to visualize and really see it. I find that the flexibility method is better in that situation because, again, a little easier to conceptualize. Okay, a little confused about what we're trying to find. Okay, this is the original problem here. This is a bar that is tightly fitted between two supports. It cannot move. And we applied a load to it, but some of the load goes to this support, some of the load goes to that support. How do you figure out how much load goes here, how much load goes here? That's what we're trying to find. This is an indeterminate problem. So how do I determine how much load is in BC, how much force is in AB? This is my answer. 2.4 kips is in AB, minus 3.6 kips or compression is in BC. That's what we're trying to find.
Now, do we have to draw the diagrams as well?
I highly suggest it. I highly suggest it. Let me go back up a few slides. Here, right here. I have found that students have been confused about this equation, the application of this equation. And it may seem straightforward, PL over AE, but this has led to a lot of confusion. And the confusion I found is that each one of these terms is a segment. You may have 2 segments, you may have 20 segments. There's no limit to how many segments you can have. The only limit is that in each segment, the load has to be constant in order to use this equation. If the load is not constant, then you have to integrate it, like we said last time. But if it is constant and you have several segments, it becomes very confusing what load is in each segment. And so in the application of this equation, I've had students try to put the end reactions in here. These are not end reactions. That's the force actually in that member. And I've had folks try to solve for end reactions, plug those in here over certain lengths, and it got very confusing. So if you draw an axial load diagram, then you can measure how long this segment is at 6 kips, that goes there. How long is this segment at 0 kips, that goes there. So if I go back to where we were, so something like this, you have one segment that's 36 inches long with positive 2.4 kips. You have another segment that's 24 inches long at minus 3.6 kips. This diagram makes it super simple to plug into that equation term by term. Was that too long? Should I just said, no, you don't have to if you don't want to?
No, that's fine. Thank you.
Okay. Now, the last part of this is we can find the final position of B. So node B is getting moved around a little bit because this section is in compression, this section is in tension. So this is going to stretch a little bit. This is going to compress a little bit. So how do I figure out where this is? Well, again, delta B is PL over AE. So FAB times LAB over AE gives me, so I found that this section, just like I was just talking about, what do I plug into this equation? Well, that axial load diagram tells you that from A to B, you have 2.4 kips over a 36-inch length. So that gives you, and this is all positive, so 0.00149 inches. It's positive, so it's in tension, so it's stretched out to the right. You could double check this by confirming that FBC LBC over AE, which according to the axial load diagram is minus 3.6 kips over a length of 24 inches, gives you minus 0.00149 inches. These had better be the same because node B is node B on this side or that side. It's the same point. So the same point had better move by the same amount when you calculate it from the left or to the right. And the deflection found from segment AB matches that found from segment BC. Thus, compatibility has been checked. And that's what we mean by compatibility. Okay, so that was indeterminate axially loaded members. Any questions on that material? Okay, so again, we have the flexibility method or the compatibility method. Final answers would be 2.4 and minus 3.6. Yes. Yes. If the question was, what are the forces in A, B, and B, C, then that would be, those answers would be correct. If I was looking for reactions, then the answer would have been the reaction at A is 2.4 kips to the left. The reaction at C is 3.6 kips to the left. Does that make sense? Okay, good. All right, so that puts this one done. And now we have this one. Okay, so lecture 8 for tonight. Tonight's lecture is about thermal stress. So I think pretty much everybody knows this, but changes in temperature will cause materials to contract or expand, right? We all have a common experience. We know that when stuff gets hot, it expands, and when stuff gets cold, it contracts, with a few notable exceptions. What would be the most obvious exception to that rule be? Yep. Water is an obvious exception to the stuff gets warmer, it expands rule. But that's only when it has a phase transformation from liquid to solid. But as everybody knows, ice expands and water when it freezes. Otherwise, though, water does follow the same expansion contraction. When you warm up water, it does expand. When you cool water, it does contract. It's just very, very minor until it gets to steam or ice, and then it's very dramatic. Okay, but that's it. That's all I'm going to talk about water. Just about every mechanical or structural material that we're going to be taking a look at follows that you warm it up, it expands, and you cool it down, and it will contract. The problem is, I guess there's two problems. The problem is that different materials will expand or contract at different rates. And the other problem is if you change the temperature of a material that is restrained. If you have a restrained member or beam or column or whatever, and you warm it up or cool it down, it can develop enormous internal forces if you prevent it from doing what it wants to do. Okay, here's the equation. Super simple, right? Delta T is equal to alpha delta T L. That's it. That's the one equation for tonight. Any questions? Okay, see you all tomorrow. No, just kidding. But that is the only equation. It's just how do we apply it is where the skills come in. So this equation, delta T, alpha delta T L, where delta T is a change in material length, this is inches or millimeters, due to change in temperature. Alpha is a linear coefficient of thermal expansion. It is material specific, and the numbers can be found on your textbook back cover. It is measured in inch per inch over degree Fahrenheit or millimeter per millimeter over degree Celsius. Delta capital T is the change in temperature. So delta T is negative for a temperature reduction and is positive for a temperature increase in temperature. And of course, delta T is measured in degrees Fahrenheit or degrees Celsius, depending on which system you're working in. But you got to make sure you have the right coefficient. Alpha has to match your degrees Fahrenheit or Celsius because for obvious reasons. And L is the original member length before you had a temperature change. So this equation here, as I said, that's it. That's the only equation. This equation here calculates a change in length due to a change in temperature. Any questions so far? Okay, so examples. Example number 1. If I have a steel bar fixed to a wall, as shown, and so this bar is 10 feet long, it's only fixed at one end, it's free to expand. The bar is A36 steel. The original temperature, T1, is 80 degrees Fahrenheit, and we changed the temperature so that it is only 10 degrees Fahrenheit. So the question is, what is the change in length of the bar from 80 degrees to 10 degrees? Solution. So delta T is alpha delta TL. From the back cover, I can look up that alpha is 6.60 e to the minus 6 per degree Fahrenheit from the back cover. Delta T, it's always going to be T2 minus T1. So in this case, it's going to be T2 is 10 degrees minus the original 80 degrees is minus 70 degrees. My length is 10 feet, but I'm going to convert that to inches. So I multiply 12 inches per foot, and I get 120 inches as my original length. So my expansion or contraction, my change in length, is 6.6 e to the minus 6 per degree Fahrenheit times minus 70 degrees minus or times 120 inches. And you can see that this is per degrees and this is degrees. So the units of the degrees drops out. The strain was inch per inch, that drops out. What you're left with is just inches. And so we get minus 0.055 inch change. So as this thing goes from day to night, this bar will actually shorten by 0.055 inches. And we box the answer, and that's example 1. Any questions?
I do have a question, actually, Professor.
Yes, please.
So basically, is there going to be a time factor in this later on in this course, or no? Like, however much it like changes over time, or is that kind of a broad question?
No, that's a good question. No, there will not be a time factor in this. And hopefully I'm giving you the right answer, but the answer that there will not be time is that either one, time plays in when you're talking about energy. So an expenditure or an absorption of energy, one or the other, when you talk about giving off or taking in energy over time, that is power. And power, I think there actually is going to be like one little section on power, and that's it for the whole course. So it's just a quick little glimpse at power, but otherwise we're not looking at power for this course. The other thing about being with time is we assume for basically the entirety of this course, everything we're doing in this course, we assume that every problem starts and remains in static equilibrium. Every problem. So it started with static equilibrium. We changed the temperature, or we put some forces on it, or we did something, and then it's still in static equilibrium. So if that is the case, then time does not play into this, because time only plays into it when things are moving, and that's a whole different course. That would be dynamics. Does that actually, did I answer your question?
Yeah, actually, I was just curious, so thank you.
Yeah, okay, cool. It is an interesting question, though, when it comes to thermal. Like, if you change the temperature, how long does it actually take the material to respond to the change in temperature? Hadn't really thought about that. But then that gets into some really interesting topics about the propagation of heat through a material. So in other words, that bar we were just talking about, if you were to like apply heat to just one end of it, then that end would pretty much instantaneously expand. But then the heat would have to propagate from the one end down to the other end. And at some point in time, there's your time, at some point in time, the whole bar would normalize to one temperature and it would expand accordingly. But until that time, some of the bar is warmer than some of the other bar. And so the expansion is a function of time because the heat propagation is a function of time. And that whole subject is about all I'm going to talk about because I remember doing it in advanced differential equations and it didn't make me very happy. So I'm trying not to relive those memories. Any other questions at this time? Okay. So we found that the change in length was 0.055 inches. And that may not seem like much, right? That's if you kind of hold your finger and your thumb together and you put them as close as you can get them and still see daylight through it. That's about what that distance is. And that may not seem like much in length over a 10-foot bar, but if that bar was restrained from movement, if you actually solidly welded that bar to something and it cannot move, then the forces inside of that bar might be a little surprising. So if I took that A to C and it's now fully restrained at both ends, well, now we got a whole different story. Then very large restraining forces can develop in that member just from temperature changes. Okay, so now we're going to go to example number 2. If we have a restrained bar as shown, okay, starting to look kind of familiar, but I've got one material from A to B over 36 inches. I have another material from B to C over 24 inches. Okay, so from A to B, this is what's known, according to the back cover of the book, C83400 red brass. It has a Young's modulus of 14,600 KSI, and it has an alpha 9.80 e to the minus 6 per degree Fahrenheit. The area is 1.75 inches squared. From B to C, I have 2014 T6 aluminum. Modulus is 10,600 KSI, and alpha is 12.80 e to the minus 6 per degree Fahrenheit. Area is the same, 1.75 inches squared. T1, the original temperature is 50 degrees. T2 is 120 degrees. What is the induced force in this rod due to thermal expansion? Or I should actually say restrained thermal expansion. Solution. Okay, so as I mentioned a moment ago, we can use the compatibility method or we can use the flexibility method. We're going to use the compatibility method here to find our restrained deformations. We're going to break each member into individual free sticks, find the thermal deformation of each. Mario, T1 is 50 degrees, T2 is 120 degrees.
Thank you. Sorry about that.
No problem. You know what? I forgot to note that both of these are Fahrenheit. 50 degrees Fahrenheit, 120 degrees Fahrenheit. Okay. So first of all, our delta T. Delta T is T2 minus T1. So in this case, it is positive 70 degrees. So the temperature has been raised by 70 degrees. And now we're going to break it into two individual sticks. First stick is A to B, and we're going to find out what the deformation, the T is for temperature, and A to B. So this is delta T for temperature, member AB. And delta TAB is alpha delta T L, which equals 0.0247 inches. The temperature was increased, so A to B expanded. So this is positive for expansion. Let me clarify that for a minute. I'm a little confused. Somebody wants me to stab somebody?
No, it's just the delta TAB. It looks like stab.
Oh. Okay, good. I didn't want any violence here. Delta TAB is positive not because it's going to the right. It is positive because it is expanding. If delta TAB was negative, it would be contracting. Okay, so the sign convention here, it's not to the left, it's not to the right, it's expanding or contracting. Positive is expanding. Okay, so now we look at our other stick. We free it up in the middle here at B. So I have delta for temperature, stick BC. The alpha is 12.8, delta T is 70, and the length is 24. So I have an expansion of 0.0215 inches. And again, it's positive, it's expanding. Okay, so overall, the whole rod from A to B to C wants to expand. Makes sense? It's gaining temperature. The temperature went up. So the whole A to B to C rod would like to get longer. It'd like to expand, but it can't. It's wedged between these two walls. But if it could, how far does it want to expand? The whole rod. Well, the whole rod is the sum of both deltas, delta TAB plus delta TBC, which is 0.247 plus 0.0215. So the whole rod, all 5 feet of it, wants to expand 0.462 inches. And this is important. That's why I'm making a point of this, because if it was free to expand, this is the total increase in length. But it's not free to expand. So that's where this is going to come in.
Professor, quick question. Wouldn't they be expanding into each other since they're connected? Wouldn't they be like pushing against each other, and wouldn't it kind of like cancel out? Or does that not work like that?
No, it does. And that's exactly where we're going to go. If C and A were just rollers, then the whole thing would just expand by 0.462. But they're not rollers, they're fixed. So as the rod tries to expand, AB and BC are just going to squish into each other. And what that's going to cause is a force in AB and a force in BC. But AB and BC are not the same material, and they're not the same length. So they're not going to squish and cancel each other out equally. One of them is going to squish, that's a technical term. One of them is going to squish a little bit more, and the other one's going to squish a little bit less. So node B is not going to end up exactly where it started from. It's going to move a little bit. But yes, the rod is going to basically squish into each other. So delta T is equal to 0.0462 inches is how much rod ABC would expand if it were free to do so. But rod ABC is not free to expand, it is restrained. So now we have to find our restraining forces. Okay, so if I take a free body diagram of AB again, I have this force in rod AB that is the force at B, and it's R for restraining force. And I have a delta RAB. I have a delta due to the restraining force in AB. Delta RAB is not equal to delta TAB necessarily. Mustafa, is there any bent end result? You mean, will the rods bend? Is that the question?
Yes.
Okay. Yes, they will, but we don't know if they will or not until we get almost to the very end of our class, because that's what's known as buckling. So, but yeah, you're absolutely right. If you induce a large compressive force in the material and it exceeds the buckling load, then the material will buckle. Yes, but we'll get to that. Well, we're not going to finish this time. We're going to carry this over into next lecture. But I got a nice picture of that at the end of next lecture. And then almost, if not the very last lecture of this whole semester, we'll talk about buckling.
Thank you, Professor.
Okay, so, but I want to be clear here that we have some induced force. We don't know what it is yet. And that induced force is going to try to compress member AB by delta RAB. But delta RAB is not equal to delta TAB. It's something different. So this restraining force here, FBR, is equal to delta RAB times the area times the Young's modulus over L. So this is going to be delta RAB. I don't know what that is yet, but I know the other three. So I can solve it in terms of delta RAB. So the rest of all this stuff whittles down to 709.7 kips per inch. And likewise, I can do a free body diagram of BC. And due to this force FBR, the force at B due to restraining forces, I have this delta RBC. And delta RBC, or FBR, again, is equal to this deformation times the area times Young's modulus over the length. And that equals delta RBC times the area times Young's modulus times the length of material BC. And remember, the Young's moduluses are not the same. This one was brass, this one was aluminum. But and that equals 772.9 kips per inch times delta RBC. But what is the same? What is the same is the induced force in this rod, because there is no external loading on this rod. The induced force in this whole rod is the same force. So the force that is compressing AB is the same force that is compressing BC. FBR is the same as FBR. Therefore, what we can say is delta RAB plus, this is the deformation due to the restraining force in AB, plus the restraining force in BC, plus my original thermal expansion, all equals 0. However much the rod wants to expand is exactly canceled out by the squish in AB and the squish in BC. It has to, because the end product is the exact same length as the original product. Therefore, delta RAB plus delta RBC is equal to this total thermal expansion, 0.462. So now if I equate FBR, my restraining force was 709 times delta RAB, or it's 772.9 times delta RBC. So I can equate the two. And I can solve for delta RAB is this proportion of delta RBC. Again, same strategy as before, where I can relate by rigidities that the deformation in one rod is a proportional to the deformation in the other rod. That proportion is 1.089 delta RBC. So 1.089 delta RBC plus delta RBC is equal to, I just took this and plugged it back into here. And that's equal to minus 0.0462 inches. So delta RBC is minus 0.02212 inch, which means that delta RAB is 1.089 times that here equals minus 0.02409. So now I have the deformation of RAB or rod AB, and I have the deformation of rod BC. So the forces, the restraining force, I could use either one of these equations because they're equivalent, but I'm choosing to use this one. So I can plug RAB into this equation here, and if the restraining force is minus 17.07 kips. It is negative because, or I'm sorry, the sign of it is negative because the deformation was negative. So that means because this is negative, that force is in compression. It's not to the left, it's not to the right, it's because this is negative, the force is compressive. And intuitively, that should make sense. If you take a rod and you hold it between 2 points and you heat it up, you would expect to get compressive forces in that rod. For the end reactions, I will draw a free body diagram of A to B. So the restraining force at B was this 1707 RAX. Sum the forces in the x direction equal to 0. I get RAX is 17.07 kips to the right. And again, internal forces are compression or tension. External reactions have an arrow to tell you which way they go. Find the end reactions. I draw a free body diagram of BC. Here's my compressive force on rod BC. Here's my end reaction. Sum the forces in the x direction, and I have 1707 minus RCX. So RCX is 1707 kips to the left. And I can draw an axial load diagram, and the load is constant. Why is the load constant? Anybody?
There is no internal forces.
Exactly right. The load is constant because there are no external loads on that rod. So there's nothing to change the constantness of the internal force in that rod. So this is my axial load diagram. And you can see this is a fairly substantial load on a rod that's, you know, roughly that big or so, 1.75 inches squared of aluminum. And the temperature didn't increase by that much. It was only 70 degrees. And here we have 17,000 pounds induced into that rod. And we box our answer. And that is the end of that example. Any questions? Okay. We have a few minutes. I know I am not going to make it. I'm not going to make it anywhere near through this next example. And I have another example after that. So I'm going to save those for Thursday. But we have roughly 10 minutes now.
Professor.
Yes, please.
This is a little bit off topic, but what you mentioned about the buckling,
Uh-huh.
when let's say you're testing a member for like to create like a shear strain diagram,
Uh-huh.
when it buckles, how is that represented on the diagram? Like, whereas is that the proportional limit or the ultimate stress or the fracture stress point on the diagram?
I love that question. That's a great question. You're still able to see what I'm drawing here?
Yes.
Yes.
Okay, so that's the elastic portion. That's the yielding portion. And then we have this strain hardening region. And then at some point you have fracture, okay? So this could be tension, this could be compression. If it is steel, then this would represent a stress strain sample in compression for steel. But that sample is only representative of a sample that is wide enough and squat enough that it will not buckle. Buckling is a function of the slenderness ratio. So the narrower it is, the more tall and slender it is, the more that it's apt to buckle. So if I go from a very squat and robust section that won't buckle to something that might have a tendency for buckling, then what you might see is at the strain hardening region, it might start failing sooner than if it was not able to buckle like this. But if it gets to be more slender, you may have a sample that barely makes it to yield and then starts failing like so. Or you could have a sample that is really, really slender and you're not even going to make it anywhere near yielding before it buckles, and it would look like this. So the stress strain diagram for buckling changes the overall behavior to something like this.
Thank you.
Okay, perfect. On the tension side, of course, nobody ever buckles in tension. So the tension curve would remain unchanged, but it's on the compressive side that you will start seeing this sort of a behavior, and you'll see a maximum stress that may or may not even get to the yielding stress. This is a very important concept in structural engineering that we need to be very careful and cognizant of how slender we're making things, because they may not carry the load that we're expecting them to carry.
So, Professor, it would be only with the rising of the temperature.
More specifically, it would be only with a compressive load. So if a rising temperature creates compression, then yes. Yes. But if a rising temperature in some way creates tension, then that would be different. Okay, and then Nicholas had a question. I don't want to ignore you, Nicholas. We were looking for FBR. Yes, we were, but that wasn't, that's not my eraser. There's my eraser. Excuse me. Let me go back. Okay. Yeah, FBR, but really what we're looking for, the question was stated, what is the induced force if I had this restrained condition? And this is the induced force right here, but we solved it by solving for FBR here. It's a slight nuance, but it wasn't actually FBR that we were looking for. It was this force here. Does that make sense? Okay, great. All right, do I have any other questions? we're gonna not take the presentation any farther than this tonight. We got 5 minutes. It was my intent, by the way, that whatever time we have next lecture, after I finish the rest of thermal stress, we're not going to just plow straight into the next topic. That will be done a week from today on Tuesday. It was my intention that whatever time we have left over on Thursday, our next lecture, after we finish thermal stress, we would just dedicate some of that time to go over, because it's going to be your first midterm a week from Thursday. So I was going to talk about that for a little bit after we finish up this topic of thermal stress. So having said that, do I have any other questions for tonight?
Just again on the, the squish factor.
Yes.
So we found the restraining force that basically like they act against each other to hold it in place, right?
Yes.
So will we need to actually go through and find what the actual deformation is between the two?
You might, and you certainly could. You certainly could, because what you could do now, I didn't carry it all the way out in this problem, but I did it in the last problem. Now that you know what the force is from A to B, you could use the delta is equal to PL over AE equation to find what the actual deformation is on this rod. And then you could do the same thing for B to C and see what the deformation is on that rod. And then that would give you where B is in the middle.
So you would just find the difference between the two?
Actually, what you would do, oh, that's a good question. Think about that for a second. Actually, what you would do is you would calculate what is the, let's just take section AB. And you know what? Let me get back to this in just a second. That's a great question. But Dima, no, the homework, the midterm is not going to be up to homework 5 necessarily. It's not up to homework 5. The midterm is going to be on chapters 1, 2, and 3. So you can go by that guide, not by the homeworks, but by chapters 1, 2, 3. Natalie, oh, I'm sorry. Okay. Somebody asked me, no other study guide outside the homework is given, right? Look on Blackboard. I've been posting study guides. Yes, sorry, I blew that one, but look on the Blackboard, and I've been posting handouts. Those handouts augment what you're reading in the text. What you're reading in the text and the handouts are augmented by either the YouTube version of this lecture or by the PowerPoint version of the lecture that I'm putting on Blackboard as well. Okay, now back to Mario's question, which is a good question. I think I can do this in 2 minutes. If you just look at rod A to B, you have a force in rod A to B. That force is compressive, so that force will tend to make the length of A to B smaller. But you also have the temperature change in rod A to B, and that temperature change would tend to make the rod longer. So what you have to do, if you want to find out what the exact length of A to B is after it's all said and done, and it's not going to be the 36 inches that you started with, then what you do is you find the expansion of A to B by using the alpha delta T L equation, and then you add to that the compression of A to B with the PL over AE equation using minus 17.07 kips as your P. They nearly cancel each other out, but not exactly. So that's how you find where node B is. And we will talk about this more next time because we're going to do a little bit more of that calculation next time.
Okay, thank you.
Okay. And on the chat here, yeah, no, thermal stress is in chapter 4. The axially loaded members between two fixed points is also chapter 4. We're going to go through chapter 1, 2, and 3, and we'll talk about that a lot more on Thursday. So everybody have a great evening, and we will see you on Thursday.
Thank you, Professor.
Thank you.
Thank you.
Professor.
Okay, thank you, everybody. See you on Thursday.